Vivek, you're not audible.
Maybe, sir, you can unmute. You are muted.
Yeah. Is it audible now?
Yes, yes. Yeah.
Oh, sorry. Yeah. I'm going to discuss about geometric phases today. And I begin with the question that is it unique? And this talk is based on the preprint, archive preprint, which is whose address is mentioned here. Yeah.
Excuse me, sir.
Based.
Hello. Excuse me, sir.
Yeah.
So there is a small window right at the at the right bottom part. So we just is there any way that we can get rid of that?
Okay.
Because it's covering the the lower part.
Is it better now?
Yes. Yes.
Okay. Thank you. Yeah. So this talk is based on this preprint, archive preprint, which was uploaded in January, where you will find detailed references on the subject, as also detailed mathematical expositions pertaining to this talk. I was told that this talk is attracts lot of young students who want to get into quantum physics and its applications. So I've tried my best to keep the content palatable to the youngsters. So apologies to the more advanced workers if they find it to be too elementary. So let us begin with this simple experiment. Which anyone, like typically anybody who has any exposure to quantum physics would have come across in first year, let's say, or second year of study of interferometry. So we start with suppose we are given a source, which produces particles, let's say electrons or photons or some neutrons or something, which are quantum particles, by the way, and it generates them in a fixed state psi. Can be for light, it can be a fixed polarization state at a fixed wavelength, like the way you have it in laser. So we know all the relevant quantum numbers. We know exactly what that state is. Source that if you repeat this experiment many times, you always get the same state psi. I mean, you always get the same particle. You always get the particle in the same state psi that comes out of it. And if you put these beam splitters, which are like semi-silvered mirrors, and then you can have photons traveling through one path, psi1, and reaching the detector. On the other hand, if you have beam splitters and mirrors, completely silvered mirrors, then you can have photons traveling to the second path and reaching the detector. In which case, because of time evolution, the initial state psi that reaches here would be changed to psi2, and the state psi on this arm will sort of change to psi1. We know that system would typically evolve, in time. And in the detector region, typically, you have a photographic film. In case of in good old days, there were photographic films. Now these days you have CCD cameras or photomultiplier tubes, and what they measure is actually the intensity. In case of light, it is intensity. In case of electrons, it's the number of electrons reaching a pixel of CCD. And basically what one is measuring is mod psi square. When we say intensity, what we're actually finding out is mod psi square, and where psi is actually the superposition of psi1 and psi2. Okay, so the idea is that you exploit the freedom available in quantum mechanics, that of linear superposition of states, and you measure the resultant intensity, or the mod square. If you want to use this language of vectors, then you measure the squared norm of the resultant vector. Okay, and when you attempt to do that, what you actually find that this mod squared can be written as, you can break it up. You can write it as sum over sum of two intensities due to psi1 and psi2 plus twice the real part of the inner product of psi 1 and psi 2, which is sort of elementary. You can break it up and see. And because in general, the inner product of psi 1 and psi 2 is a complex number, because quantum mechanics, we work with complex vector spaces. I think it's pretty much familiar to young people. So this real part can be, can be written as, the mod part plus an angle, cos of an angle. And that angle is the argument of the inner product. So if we would not have this part, as elegantly discussed by Feynman in his third volume, Lectures in Physics, third volume, then in classical physics, we typically don't have this third term, and we only see this addition of intensities taking place. For example, if you were to do this experiment with bullets, as Feynman has suggested, or with cars or honeybees or something like that, which are macroscopic objects, but they don't behave quantum mechanically, then you don't see this interference term. But when you do it with photons or with electrons, which are coherent, then you see an occurrence of a cosine of an angle. And it is this cosine term that gives rise to the intensity, extrema, the famous interference patterns in the experiment. Because of this periodic variation as you change phi. So this phi, because you are measuring, you are defining this phi between these two vectors, between two states, as argument of the inner product, you call it the relative phase. So it is like, it is phase of psi 2 with respect to psi 1 in some sense, but we'll come to that, why it is relative. And the point is that as you increase or decrease the length of one of these arms, typically you increase the length of this arm or this arm, you actually you change psi 2 slightly, and as a result, you are able to shift through the extrema patterns. Okay. Another way of seeing that this is the relative phase is that if you change psi 2 with an overall phase. Now see, these overall phases are a bit of a murky beast, sort of, in quantum mechanics. If you have an isolated system, then psi and a phase multiplied with psi, they represent the same quantum state, because all the averages, they correspond to same density matrices. But when you are in superposition, when you are in a state like this, and then if you put a factor here, then it is no longer the same state. Or in other words, if you put an exponential factor here, your relative phase will change by an amount theta. By this, theta shifts the relative phase. Hence, it is actually measuring the relative phase change between psi 1 and psi 2. So that is the origin of the relative work. But it's very, very important concept, because in some sense, all the magic of quantum mechanics is sort of encoded or sort of capsuled in this beautiful small concept. So all the beautiful magic that you see in most experiments, at some level or the other, they are exploiting relative phases. Okay. And typically, so Pancharatnam, who was a nephew of Sir C.V. Raman, in 1950s was asked by C.V. Raman to study light interference in crystals. And in that course, he started asking these very simple questions of what do you mean by interference? What do you mean by interference between light, which is in different polarization states? Light, when it is in different polarization state, the theory of interference was not known by then. So he worked it out, and he came up with a criteria. He said that if you have two states, psi 1 and psi 2, such that argument of their inner product is 0, then you say that they are in phase in the sense of Pancharatnam. What essentially he's telling us that it corresponds to the intensity maxima. That is, when this term is absent, Yes, this is the maximum of intensity that you are going to find. Okay. Oh, sorry. When this term is 1, I made a mistake. When cosine is 1, that is the maximum intensity what you are going to find. And this is the famous Pancharatnam in-phase condition. Pancharatnam, when he was studying propagation in crystals, he came up with a, you can say a phenomena where you have 3 interferences taking place. 3 interference as in you have interference of 3 states which is taking place. So you have psi1 which is interfering with psi2, giving you something. You have psi2 interfering with psi3, giving you something else. And you have psi3 interfering with psi1, giving you something else. And the outcome in the crystal was due to all 3 of them simultaneously. So he considered a scenario. He asked this question that suppose I start with a simple situation that psi1 is in phase with psi2, and psi2 is also in phase with psi3. So this is also in phase with psi3. Does that imply that psi3 is also in phase with psi1? In other words, if the relative phase between psi1 and psi2 is 0, if the relative phase between psi2 and psi3 is also 0, that relative phase between psi3 and psi1 is also 0. Very soon, very quickly, he was able to find a counter example, and in general he showed that that's not the case. So the in-phase condition, mathematically speaking, is not a transitive quantity. It does not have the transitive property. So in order to measure the deviation from this in-phase condition, he said that let me add all the relative phases, and if you just add them, all these 3 quantities using the properties of argument, you can rewrite it in a nice symmetric form. So you have 3 inner products in the numerator, inner product of psi1, psi2, inner product of psi2, psi3, and psi3, psi1. And you can, for normalization considerations, you can also divide it by a positive number, which is the squared norm of all the vectors. It doesn't matter because it's a positive quantity anyways, so argument is not going to change. But it for future purpose, it was very helpful to write it in this way. And he called this quantity a geometric phase. He didn't use exactly the word geometric phase, but now it is called the geometric phase. So if gamma is equal to 0, then you say that all these, mutually all these vectors or all these states are in phase condition. If it is non-zero, then at least one of them is not in phase with another, and the value, how much it is away from the in-phase condition, that is the value given by gamma. Now, interestingly, if I make a transformation, if I change the angle, if I multiply an overall phase to all these vectors, then the value of gamma does not change, because phase coming from psi1 gets cancelled with psi1 from here. Psi3 here gets cancelled from the phase coming from here. Psi2 with psi2 coming from here. So all these phases get cancelled. That is the, so in some sense, this phase is fundamentally different from the relative phase. Although it is sum of 3 relative phases, as we saw, as we see here, it is actually sum of 3 relative phases. But mind you, relative phases were changing as you changed, multiplied the vector with a global phase, it was changing. But here, this object does not change. So in some sense, this object is invariant. So in some sense, this is a fundamentally a different object at a different pedestal. And now we understand, later it was christened as the geometric phase. Well, it is possible to write this in form of density matrices. Now, mind you, here we are in this talk and in context of my work, I would always confine to the pure states. It is possible to work with mixed states, but I am not venturing into that direction. So if you are more comfortable with density matrices, then all you have to do is you have to construct the corresponding density matrices for these 3 states, take their product, find its state, and find the argument. That is the geometric phase. So it is not possible to define the relative phase. This relative phase cannot be defined in terms of density matrices. You can check, it's not possible. You don't have enough freedom. That is the fundamental difference between the geometric phase and relative phases. And appreciation of this difference has given an immense amount of insight in the working of quantum mechanics in subsequent years. By the way, feel free to interrupt me and ask any questions. Okay, so I'm not sure how much people are familiar with these things, so feel free. Fine with me. Now, suppose instead of 3 states, you have n states. You have in your state space, in your Hilbert space, you have psi1, psi2, psi3, and n states. Then also you can ask the same question, that are they mutually in phase with one another? And in order to find out yes or no, you would write a similar generalization of this expression, psi1 with psi2. You define a geometric phase where you consider inner products of psi1 with psi2, psi2 with psi3, and so on and so forth till psi n minus 1, psi n with psi1, and divided by the inner squared norms of the corresponding vectors. So that sort of is the general expression for the geometric phase. Typically, or in most cases in physics, we are not interested in such scenario. We are interested in scenarios where you start with a particular state and that state evolves as you change a parameter. Like, for example, you have constructed a system in some state. You have a particle in a box or something, and you have an initial state, and then you allow it to evolve, in time. And if you have a wave packet, it evolves, it spreads, and it does whatever it has to, depending on the Hamiltonian. And after a time t, you ask this question that what is the state of this system? And here we would ask this question, that what is the phase acquired by the state after some time? So what you do essentially is that you say that this psi1 that I'm referring to is actually psi evaluated, or state of the system at time s1. S1 can be 0. Psi2 is the state of the time at time s2, and let s2 be after delta s evolution. And we are looking at uniform time steps, like psi3 would be the state of the system after 2 s evolutions, like s3, and we define s3 to be delta s times 3 minus 1 s2. Or in general, I define psi subscript j to be psi at time sj, and sj is j minus 1 into delta s, and delta is some small time step, like 1 second or microsecond, depending on what physical system you're talking about. And if you take the limit delta is tending to 0, you take many, you let n to be large, that delta is small, in such a manner that delta s into n is a constant. Then this expression, you can work it out. It's fairly straightforward, or you can check up my manuscript. You find that this expression sort of simplifies to this form. So you have one term, which is the argument of psi at t, comma psi 0 divided by square norm of psi of t, plus an integral from 0 to capital T. The integral is that of imaginary part of this object, this quantity. Quantity is essentially inner psi and derivative of psi. How psi and how rate of change of psi divided by square norm of psi. And this quantity is popularly called the Berry vector potential in literature, or sometimes it is also called the connection, just different words for now. And this is the popular expression of the geometric phase as given by Bhandari and Samuel in 1987. Famous work of on geometric phase, most general expression for the geometric phase. For later, or just for the information of the audience, the first term is typically called the Pancharatnam total phase term. The second term is called the dynamical phase. So there are many good expositions on this. Excellent one is due to Mukunda and Simon, 1993, whose reference can be found from my manuscript. I have not written it down. So essentially, what this phase is telling you that after evolution from zero to time, from zero to t, you ask how much phase my state has acquired because of evolution, and that phase is the geometric phase, and this is the viewpoint that was sort of propounded in a phenomenal work, in a celebrated work by Sir Michael Beatty in 1984. So that is how this modern subject of geometric phase came into limelight and got its due recognition from this work. Okay, so this is how the conventional, traditional, good old geometric phase is done. Now you can ask that, well, fine, what do I do with that? I am already like, why should I bother? Like, that's a valid question. First and foremost, in recent years, there has been a lot of work about understanding the condensed matter systems like insulators, conductors, superconductors, and many other systems using these geometrical ideas. So the idea is that instead of using observables or effects due to observable, you try and understand the geometry of the underlying Hilbert space, and because that's very basic, and geometry of Hilbert space, if you can understand, you in some sense know in a very basic, very fundamental way what is difference between a conductor, let's say an insulator, and there are many kinds of insulators, so how they are different. Okay, so topological insulator is one prime example where you use these ideas of geometric phases, without which you cannot understand. At least as of now, we don't know if there is another way of understanding these properties. And the geometric phase essentially probes this geometry. One can show this up. I didn't want to make this talk more mathematical one, but essentially this object is the one that is probing geometry for you. This whole object, but in more precisely, this object, which is called the connection, natural connection on the ray space. So that is sort of probing the geometry, so natural connection on the state space, which is probing the geometry of the ray space for you. Well, actually, mumbo jumbo, high-five words, but that's the punchline sort of. Well, that's fine, but are there any observable manifestations? You can ask, like, can you do an experiment and see really? Answer is yes. There have been several experiments, starting from diatomic, triatomic molecules, starting from Pancharatnam, who actually was doing experiments. Altogether, starting Ritov and Vladimirov in 1940s, they were studying scattering of light, where some of these things were observed. Arno-Bohm effect, which I'm sure many of you are familiar, is a manifestation. For quantum computing crowd, the existence of non-abelian anyons, which was in limelight since the press release from Google and Microsoft and others. So non-abelian anyons, the anionic nature and the non-abelian nature is essentially to do with geometric phase. There is no other way by which you can understand this without invoking geometric phases. Okay. More simply, the spinor nature of the Dirac fermions is due to that. The Thomas precession, if you are familiar, or the Wigner rotation in relativity, they are all, you can probe it down to this simple concept of geometric phase, their manifestations, and several other manifestations of this concept. I'm not going into more details. No. Are there any limitations? Well, but there is nothing. Everything as a as a boundary, as a limitation. So yes, there are limitations to this concept also. What is the limitation? Well, it's very basic. If we go to the definition of relative phase, where was that? Yeah. So this, we started our definition of relative phase with this, object or this object. This answer is classical one. The quantum one is hidden here. And we say that if this is non-zero, then you can define this argument of the inner product. But what if psi1 and psi2 are orthogonal? Well, if they are orthogonal, their inner product is always zero. And in that case, you cannot define a relative phase. There is no unique way of finding what phi is. Okay. So you cannot actually talk about interference in this sense when states are orthogonal. So that is a limitation of relative phase. And because geometric phase is like for 3 states, it is sum of relative phases, and geometric phase is also not defined. Nothing special about it. Yeah. So that is one very well-known limitation of this concept. Yeah. And there have been many attempts. When I was surfing through literature, I saw several attempts on my personal discussions with Professor Mukunda and Professor Samuel. I found out that many people have tried to find a way out, but there is no obvious way out. Like you can always come up with a workaround, but like it is like an artificial one. There's no natural particular reason, of why. Basically, there is no unique sort of way of finding what the geometric phase would be in such a case. You can have your answer. I can come up with my convention. Well, you can all have other answers. We can all have the answers the way we want, and the system at hand will not conform to any particular answer because you don't have interference in the first place. How do you get a geometric phase? So if you think carefully for a second, then the way out is very obvious. Well, you find that there are more observables in quantum mechanics than just intensity. See, we have been looking at interference only looking at intensity, mod psi squared. And because in our case, mod psi square was failing to capture the interference term, we sort of said that, well, we don't know the way out. But quantum mechanics is far more richer. It allows us to measure averages of observables also. So for example, you can also construct, or you can not only construct, you can measure objects like these. Like in a system, you can find what is average position of a particle, average like particle in the box. You can always ask and find these questions. What is average position? What is average energy? In hydrogen atom, for example, what is average angular momentum? And stuff like that. And you do find and you do work with them. They are physical as they can, as quantum mechanics can get. So for the younger audience, the average is if you take any observable. Oh, by the way, when I mean observable, I'm assuming that I have a Hilbert space given to me. O is a linear operator over that Hilbert space, well-defined linear operator obeying all the necessary boundary conditions. Furthermore, it is also a self-adjoint operator, loosely meaning that it's eigenvalues are real. So, and why do we want eigenvalues real? Because outcomes of our measurements are eigenvalues. So when you measure this average, it is actually a weighted sum of eigenvalues with the weights being probability. You can work it out. You can just consider the eigenstates of this operator O with eigenvalue lambda n, and you can just go through the math. Very straightforward, very elementary, but highly recommended if you are new to this subject. So my point of showing this calculation is that such averages are measurable in experiments. In experiments, you measure these probabilities, you find these eigenvalues as the outcomes of measurements, and you construct, you take many measurements following the statistical interpretation, and you construct these averages. Exactly the same way In the case of a photographic film or a CCD camera, you measure averages. Sorry, you measure intensity by making many measurements. Here you measure averages, routinely done. So now, suppose we return back to our original experiment, and instead of measuring intensity, let us measure the average for some observable O. Now, the average would read like this: that we have psi1 plus psi2, operate O onto this psi1 plus psi2 state, and take the inner product. And if you open the brackets and do a bit of math, you find that here also you have two terms. One term is the average of psi1, other is like average of psi2. Average of O in state psi1, average of O in state psi2, and then you have again a cosine term of an angle. This angle now is different from the earlier angle that we found. So because there is an O sitting in the inner product. Again, you can see that there will be interference patterns because there is an angle here. And if you change psi2 with an overall phase e to the power I theta, that theta pop out here to change this phi naught or phi O, and you will have interference pattern. But now the pattern will be different because this object is different. This object is different. This pattern will now not be seen in intensity, it will be now seen in the average of O. Okay, so keep that in mind. Like fundamental difference, very different. Again, these two terms are of classical origin. Again, you can sort of show that it's of quantum origin. So we have found out that there is a new relative phase. So for each average measurement, if you are measuring average of position, you will have a relative phase corresponding to position operator. If you are measuring, let's say, average of energy, you will have another relative phase which is sensitive to the energy. So where this O becomes Hamiltonian, and so on and so forth. Interestingly, if you take the difference of the two relative phases, namely this O relative phase and the earlier relative phase, which is this minus this, it becomes like inner product of psi1 acting on O, psi2 divided by psi1, psi2 inner product. But this object is nothing but the weak value of the observable O. I'm sure in many of the talks in this conference, you would have come across these weak values. And very interesting. They have attracted a lot of attention in the community, and a lot of work, a lot of thought has been, sort of dwelled to give meaning to the complex nature of this object. Why this object weak value is complex, And here we find that, well, it is complex because it sort of measures that the quantum mechanics has more than one relative phases, and it tells you that how this relative phase is different from the intensity one, like how much they are different. So it's very natural. Like we are not inventing something out of thin air, really. Like, we are just following very basic ideas handed over to us by the founding fathers of the subject. Okay. Again, if you have this geometry, I mean, the original relative phase equal to 0, then it does not imply anything about the new relative phase being 0. Similarly, if this new relative phase, if this object is 0, nothing can be deduced about this one, because they are fundamentally different quantities. The action of operator O changes the game. Of course, you can always find simple cases where they are related, but well, that's a special case, really. Here we are not assuming that there are any particular commutation relations or any particular like symmetries into action or any other constraints, just assuming simple free structure. So there is no connection. If the states are orthogonal, then also you can have this inner product being non-zero. And if this is 0, it need not imply that the states are orthogonal. Okay. So this paves the way to, so what we are telling here is that when you cannot define interference in intensity measurements, you better go to average measurements, average of some observable. Probably you will be able to construct a meaningful observable relevant to the physics of the problem, and you measure interference in that channel. And in that channel, you can again ask these questions that if the if the relative phase in that channel is equal to 0, then you say that psi 1 and psi 2 in that channel corresponding to that concept, they are in phase. Well, the moment you have defined this in phase condition, you can straight away follow Pancharatnam and say that, well, I can also define a geometric phase, which is nothing but sum of 3 relative phases. And I have this geometric phase. So psi 1 O acting on psi 2, psi 2 O acting on psi 3, psi 3 O acting on psi 1. And this is the operator generalized geometric phase that we sort of proposed in January this year in our work. If O becomes identity, this geometric phase goes back to the well-known one, the earlier one. But it need not. You can have other exciting situations where O is not identity. Again, if you go to the continuous case, which I had mentioned earlier, then you will have a different potential appearing, this kind, and a Pancharatnam total phase term, or different dynamical phase and a different total phase. As expected, no big deal, like just following through the math, Immediately one can ask this question that, well, is it a mathematical gimmick, some kind of trick that one is playing? Just fancy way of doing, complicating one's life and getting into, non-trivial stuff, or is it physical? Like, do you like, do you care? I mean, to show that if it has any physics, answer is yes, it is physical. So to highlight this, let me consider a simple example. Suppose you have some simple system at hand. Let's say a simple system, as in you have a particle in Coulomb potential. Let's say, simple non-realistic particle in Coulomb potential. We are interested in small time evolution, infinite evolution for infinitesimal time. So in small time, if you start with, say, state psi of 0, then you activate with this operator. I linearized the unitary time evolution operator, and you get your state after time tau, the action of identity minus this, non-trivial term, which is the Hamiltonian. Okay. Now suppose in this problem you have 3 orthonormal states, 0, 1, and 2. Some general state. They need not be any particularly like interesting states. Like they need not be eigenstates of something. Certainly, we are assuming that they are not Hamiltonian eigenstates. That's crucial right now in this example. Okay. And we suppose prepare the system in state 0, so psi 0, and then we measure, do a measurement, and we discover that after the measurement, the state was found to be in state 1. So we did measurement after time tau, and then we found that the state was in the state of the system was found to be in 1. Again, we allowed it to evolve for time tau, and then we made measurement, and then we discovered that it was in state 2. Well, again, after that, we allowed it to evolve for time tau, and again made a measurement and found that it was back in the state 0. So now that the system is back to state 0 from where we started with, we can ask this question: that what is the phase acquired by the system in this process? So it's like you went to from 0 to 1, 1 to 2, 2 to 0, you came back, triangular route, and you ask this question that did we come back with an overall phase? No. Answer is yes. You came back with a geometric phase, which if you calculate, it would be this. So it won't be this geometric phase. It's not the old geometric phase that you would have expected, because it is not even defined. So 0 and 1 are orthogonal, like 1 and 2 are orthogonal, 2 and 0 are orthogonal. So you cannot even define. Okay. So, and you can measure this. These kinds of phases are found in scattering problems. If you look at scattering theory, if you look at the third order, if you look at the Born-Oppenheimer approximation, the third order term, you do have terms which are of this kind. Also in time independent perturbation theory, the third order contribution does have terms which are of this kind. So it is like not that they are unphysical. In fact, they are far more physical, and these terms are actually contributing to the like in case of time independent perturbation theory, they do affect the energy level sort of spacing of the problem. In case of scattering problem, it does affect the scattering cross section. You know, that's what we have shown in our work. So I think I would want to summarize with this. What we find that the notion of geometric phase is very general one. Namely, for each observable, there exists a special. I mean, there exists a geometric phase for each observable. Like, give me an observable, and I will find a corresponding geometric phase for it. Correspondingly, you find that the geometry of quantum system is very, very rich. Like earlier, it was believed, or even now also, people may believe that you have a Hilbert space and you have corresponding ray space, and then you have the fiber bundle structure which connects them. And it is on the ray space you have what is called the Fubini's 2D metric. And ray space has a Kähler structure. Sorry for bombarding so many words to the younger audience, but this is for the more experienced people, the experts in the audience. So one would assume that that is it. Like if you have understood this, you have in some sense you have understood everything about a quantum system geometrically, pure states, so long as about the aspects of pure states. We find that that's not the case. It is far more richer, you know. So for each observable, for each geometric phase, there is a separate sort of ray space that you can define in a way whose geometry is very different. And we are working on the mathematical aspects of this work. Maybe the next manuscript would be out in 10 days. I'm just finalizing the final draft. So the mathematical minded people can refer to it. And yeah, so in this work, we found that the weak value of the observable plays a very important role in connecting the old and new geometric phase, the generalized geometric phase and the usual one. And the geometric phase is physical. It appears in scattering problem, in time independent perturbation theory, and many other cases as we have discussed in our work. So I think with this, I would sort of conclude and can take questions if there are any.
Yeah.
If there are any questions?
Thank you, Vivek, for this interesting talk on the geometric phase. So if there are any questions from the audience, please.
I have small clarification,
Yes,
doubt.
please go ahead.
So in getting that generalized geometric phase, you wrote that argument of psi 1 O cap psi 2 minus argument of psi 1 comma psi 2. That is as an
yeah, this one. Yeah.
How did you write that as a ratio?
See here,
Yeah.
These terms I've just written it for normalization, because I mean I'm assuming unit normalized vectors, then this will be 1. But if you don't want to assume that, then you just add them so that it's all like you have good like sort of answers. If you're state, you need not write them because you are 1 anyways. But if you don't assume, then you can write it. Well, argument of this is anyway 0. Doesn't matter because they are real numbers. The denominator is real, so argument, it doesn't contribute really.
Can you scroll down?
Yeah. Yeah.
Okay. Okay, fine. So that's like a just normalization thing, the denominator thing.
Exactly. Nothing more.
So at one place you wrote like phi naught minus phi equal to
Yeah, so that so there I wanted to just highlight. Yeah, so there I wanted to highlight that this is the weak value. When you look for the difference in the relative phases, that comes out as the argument of the weak value of the observable.
Okay. So, yeah, here
yeah,
you wrote as a ratio, right?
yeah. So and that comes from the property of argument. See, the argument is the angle of the complex number. Yeah, so you can just use that and you can write it.
So why is it called a weak value?
Because I don't know. I'm not an expert on these things, but you will find many articles on this. Or if there are any audience, any experts in the audience, they want to answer this question, why it is a weak value. Anyone, please? I don't know. I only know that well, this object is called the weak value for some reason.
Okay, thank you.
You can.
I will.
I know that there is a famous work of Professor ECG Sudarshan, and in around the same time, Whiteman and others. Very, very famous papers, but I've not understood. I've not ventured into them, so I don't want to comment. But you can follow on these papers.
Thank you.
Okay. Any further questions?
I have one question.
Yeah, please go ahead.
Thank you for your talk. It's a clarification. One can extract phase information by using quantum state tomography. So my question is, clarification question: what new information one can extract by using geometric phase approach?
See, I don't know about tomography so much, frankly. So I honestly not be able to connect up with your sort of question. But geometric phase, the conventional understanding is that you want to understand the see quantum system has this Hilbert space structure. Typically, we all study that. But the actual physical content is not in the Hilbert space. It is in the ray space, the space of pure state density matrices. And you would want to understand typically it's desirable to understand the geometry of this space. Like in case of qubits, it is known that it is a sphere. But you go to more general systems, it is not known. At least it's not very simple. So you would want to understand mathematical objects like curvature. Are there any holes inside this? And stuff like that. And in condensed matter system, you find that if this state space has topological invariants, like there are these objects called Chern classes, which you can define using geometric phase, then that decides whether your system at hand is an insulator or not. So I'm not an expert, frankly, but I don't think tomography is going to give you that information. I mean, I'm not very sure, but I mean, I'm sort of sure, but again, I'm not an expert on tomography, so it's like, but I don't think tomography alone can give you that. This is like a global topological information, which only geometric phase and the integral of it can give you.
Thank you.
Okay, if there are no further questions, I once again thank Vivek. And thank you, Vivek. It took me back to the heady days of postdoc where we were all discussing about all these things and Professor Berry's talks. Yeah. So, okay. So I guess we will move to the next speaker, cryptography in